Hi everybody and welcome to Introductory Networking. Let's begin. The aim of this room is to provide a beginner's introduction to the basic principles of networking. Networking is a massive topic, so this really will just be a brief overview. However, it will hopefully give you some foundational knowledge of the topic, which you can build upon for yourself. The topics that we are going to cover in this room are the OSI model, the TCP/IP model, how these models look in practice, and an introduction to basic networking tools. Okay, let's click on completed and move on to the next task, which is the OSI model, an overview. The OSI model is a standardized model which we use to demonstrate the theory behind computer networking. In practice, it's actually the more compact TCP/IP model that real-world networking is based off. However, the OSI model in many ways is easier to get an initial understanding from. The OSI model consists of 7 layers. The application layer, the presentation layer, the session layer, transport layer, network layer, data link layer, and the physical layer. There are many mnemonics floating around to help you learn the layers of the OSI model. Search around until you find one that you like. I personally favor Anxious Pale Shakespeare treated nervous drunks patiently. Let's briefly take a look at each of these in turn. Layer 7, Application. The application layer of the OSI model essentially provides networking options to programs running on a computer. It works almost exclusively with applications, providing an interface for them to use in order to transmit data. When data is given to the application layer, it is passed down into the presentation layer. Layer 6, Presentation. The presentation layer receives data from the application layer. This data tends to be in a format that the application understands, but it's not necessarily in a standardized format that could be understood by the application layer in the receiving computer. The presentation layer translates the data into a standardized format, as well as handling any encryption, compression, or other transformations to the data. With this complete, the data is passed down to the session layer. Layer 5, Session. When the session layer receives the correctly formatted data from the presentation layer, it looks to see if it can set up a connection with the other computer across the network. If it can't, then it sends back an error and the process goes no further. If a session can be established, then it's the job of the session layer to maintain it, as well as to cooperate with the session layer of the remote computer in order to synchronize communications. The session layer is particularly important as the session that it creates is unique to the communication in question. This is what allows you to make multiple requests to different endpoints simultaneously without all the data getting mixed up. Think about opening 2 tabs in a web browser at the same time. When the session layer has successfully logged a connection between the host and remote computer, the data is passed down to layer 4, the transport layer. The transport layer is a very interesting layer that serves numerous important functions. Its first purpose is to choose the protocol over which the data is to be transmitted. The 2 most common protocols in the transport layer are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. With TCP, the transmission is connection-based, which means that a connection between the computers is established and maintained for the duration of the request. This allows for a reliable transmission as the connection can be used to ensure that the packets all get to the right place. A TCP connection allows the 2 computers to remain in constant communication to ensure that the data is sent at an acceptable speed and that any lost data is resent. With UDP, the opposite is true. Packets of data are essentially thrown at the receiving computer. If it can't keep up, then that's its problem. This is why a video transmission over something like Skype can be pixelated if the connection is bad. What this means is that TCP would usually be chosen for situations where accuracy is favored over speed, for example, file transfer or loading a web page. And UDP would be used in situations where speed is more important, for example, video streaming. With a protocol selected, the transport layer then divides the transmission up into bite-sized pieces. Over TCP, these are called segments. Over UDP, they are called datagrams, which makes it easier to transmit the message successfully. Layer 3, network. The network layer is responsible for locating the destination of your request. For example, the internet is a huge network. When you want to request information from a web page, it's the network layer that takes the IP address for the page and figures out the best route to take. At this stage, we're working with what is referred to as logical addressing, that is, IP addresses, which are still software controlled. Logical addresses are used to provide order to networks, categorizing them and allowing us to properly sort them. Currently, the most common form of logical addressing is the IPv4 format, which you'll likely already be familiar with. For example, the one that we see on the screen is a common address for a home router. Layer 2, data link. The data link layer focuses on the physical addressing of the transmission. It receives a packet from the network layer that includes the IP address for the remote computer and adds in the physical MAC address of the receiving endpoint. Inside every network-enabled computer is a network interface card, which comes with a unique MAC address to identify it. MAC addresses are set by the manufacturer and literally burnt into the card. They can't be changed, although they can be spoofed. When information is sent across a network, it's actually the physical address that is used to identify where exactly to send the information. Additionally, it's also the job of the data link layer to present the data in a format suitable for transmission. The data link layer also serves an important function when it receives data, as it checks the received information to make sure that it hasn't been corrupted during transmission, which could well happen when the data is transmitted by layer 1, the physical layer. Layer 1, physical. The physical layer is right down to the hardware of the computer. This is where the electrical pulses that make up data transfer over a network are sent and received. It's the job of the physical layer to convert the binary data of the transmission into signals and transmit them across the network, as well as receiving incoming signals and converting them back into binary data. Okay, and now let's answer the questions. So, which layer would choose to send data over TCP or UDP? And that will be the transport layer. Okay, so we need to type 4 like this. Okay, and we submit. Which layer checks received packets to make sure that they haven't been corrupted? And that will be the data link layer. So, 2. In which layer would data be formatted in preparation for transmission? And that will be, again, the data link layer. So, again, we type in 2. Which layer transmits and receives data? And that will be the physical layer. So, we need to type in 1. Which layer encrypts, compresses, or otherwise transforms the initial data to give it a standardized format? And that will be the presentation layer. So, 6. Which layer tracks communications between the host and receiving computers? And that will be the session layer. So, number 5. Which layer accepts communication requests from applications? And that will be the application layer. So, number 7. Which layer handles logical addressing? And that will be the network layer. So, layer 3. Oops, like this. When sending data over TCP, what would you call the bite-sized pieces of data? We would call them segments. So let's type that in. Perfect. And now, research. Which layer would the FTP protocol communicate with? Okay, so we can just go to Google. Let's see. And let's Google FTP communication, let's see, communication layer like this. And here is our answer. So the application layer. So number 7, right? Layer number 7. So let's type in 7 and we submit. Which transport layer protocol would be best suited to transmit a live video? And that would be UDP. And we submit. And now let's move on to the next task, which is encapsulation. As the data is passed down each layer of the model, more information containing details specific to the layer in question is added on the start of the transmission. As an example, the header added by the network layer would include things like the source and destination IP addresses, and the header added by the transport layer would include, amongst other things, information specific to the protocol being used. The data link layer also adds a piece on at the end of the transmission, which is used to verify that the data has not been corrupted on transmission. This also has the added bonus of increased security, as the data can be intercepted and tampered with without breaking the trailer. This whole process is referred to as encapsulation, the process by which data can be sent from one computer to another. Notice that the encapsulated data is given a different name at different steps of the process. In layer 7, 6, and 5, the data is simply referred to as data. In the transport layer, the encapsulated data is referred to as a segment or a datagram, depending on whether TCP or UDP has been selected as a transmission protocol. At the network layer, the data is referred to as a packet. When the packet gets passed down to the data link layer, it becomes a frame, and by the time it's transmitted across a network, the frame has been broken down into bits. When the message is received by the second computer, it reverses the process, starting at the physical layer and working up until it reaches the application layer, stripping off the added information as it goes. This is referred to as de-encapsulation. As such, you can think of the layers of the OSI model as existing inside every computer with network capabilities. Whilst it's not actually as clear-cut in practice, computers all follow the same process of encapsulation to send data and de-encapsulation upon receiving it. The process of encapsulation and de-encapsulation are very important, not least because of their practical use, but also because they give us a standardized method for sending data. This means that all transmissions will consistently follow the same methodology, allowing any network-enabled device to send a request to any other reachable device and be sure that it will be understood, regardless of whether they are from the same manufacturer, use the same operating system, or any other factors. Okay, and now let's answer the questions. How would you refer to data at layer 2 of the encapsulation process with the OSI model? The answer is frames. How would you refer to data at layer 4 of the encapsulation process with the OSI model if the UDP protocol has been selected? And the answer is datagrams. Oops, my bad. Datagrams. Like this, okay. What process would a computer perform on a received message? And the answer is de-encapsulation. Perfect. Which is the only layer of the OSI model to add a trailer during encapsulation? And the answer is the data link layer. Okay, and the last question. Does encapsulation provide an extra layer of security? A. Perfect. And now let's move on to the next task, which is the TCP/IP model. The TCP/IP model is, in many ways, very similar to the OSI model. It's a few years older and serves as the basis for real-world networking. The TCP/IP model consists of 4 layers: application, transport, internet, and network interface. Between them, these cover the same range of functions as the 7 layers of the OSI model. Note, some recent sources split the TCP/IP model into 5 layers, breaking the network interface layer into data link and physical layers, as with the OSI model. This is accepted and well known, however, it is not officially defined, unlike the original 4 layers, which are defined in RFC 1122. It's up to you which version you use. Both are generally considered valid. You would be justified in asking why we bother with the OSI model if it's not actually used for anything in the real world. The answer to that question is quite simply that the OSI model, due to being less condensed and more rigid than the TCP/IP model, tends to be easier for learning the initial theory of networking. These two models match up something like this, and yes, we can see that on the screen. The process of encapsulation and de-encapsulation work in exactly the same way with the TCP/IP model as they do with the OSI model. At each layer of the TCP/IP model, a header is added during encapsulation and removed during de-encapsulation. Now let's get down to the practical side of things. A layered model is great as a visual aid. It shows us the general process of how data can be encapsulated and sent across a network. But how does it actually happen? When we talk about TCP/IP, it's all well and good to think about a table with 4 layers in it, but we're actually talking about a suite of protocols, sets of rules that define how an action is to be carried out. TCP/IP takes its name from the 2 most important of these: the Transmission Control Protocol, which we touched upon earlier in the OSI model, that controls the flow of data between 2 endpoints, and the Internet Protocol, which controls how packets are addressed and sent. There are many more protocols that make up the TCP/IP suite. We will cover some of these in later tasks. For now though, let's talk about TCP. As mentioned earlier, TCP is a connection-based protocol. In other words, before you send any data via TCP, you must first form a stable connection between the 2 computers. The process of forming this connection is called the 3-way handshake. When you attempt to make a connection, your computer first sends a special request to the remote server indicating that it wants to initialize a connection. This request contains something called a SYN, short for synchronize, bit, which essentially makes first contact in starting the connection process. The server will then respond with a packet containing the SYN bit, as well as another acknowledgement bit called ACK. Finally, your computer will send a packet that contains the ACK bit by itself, confirming that the connection has been set up successfully. With the 3-way handshake successfully completed, data can be reliably transmitted between the 2 computers. Any data that is lost or corrupted on transmission is resent, thus leading to a connection which appears to be lossless. We're not going to go into exactly how this works on a step-to-step level, not in this room at any rate. It is sufficient to know that the 3-way handshake must be carried out before a connection can be established using TCP. History. It's important to understand exactly why the TCP/IP and OSI models were originally created. To begin with, there was no standardization. Different manufacturers followed their own methodologies, and consequently, systems made by different manufacturers were completely incompatible when it came to networking. The TCP/IP model was introduced by the American Department of Defense in 1982 to provide a standard, something for all of the different manufacturers to follow. This sorted out the inconsistency problems. Later, the OSI model was also introduced by the International Organization for Standardization, or ISO. However, it's mainly used as a more comprehensive guide for learning, as the TCP/IP model is still the standard upon which modern networking is based. Okay, and now let's answer the questions. So, which model was introduced first, OSI or TCP/IP? And the answer is TCP/IP. Okay, so let's type that in. TCP, oops, my bad. Let's see, /IP, like this. Perfect. Which layer of the TCP/IP model covers the functionality of the transport layer of the OSI model? Full name. Okay, so that will be the transport layer. Transport like this, and we submit. Which layer of the TCP/IP model covers the functionality of the session layer of the OSI model? And again, we need to type in the full name. So the answer is the application layer. So we type in application. Perfect. The network interface layer of the TCP/IP model covers the functionality of two layers in the OSI model. These layers are data link and again, we need to provide the full name. So the answer is the physical layer. Physical, let me see, physical like this. Okay, and we submit. Perfect. Which layer of the TCP/IP model handles the functionality of the OSI network layer? Okay, and the answer here is Internet. Perfect. What kind of protocol is TCP? And the answer is connection-based. Okay, so let's type that in. Okay, and what is SYN short for? And that will be synchronize. Let's see, synchronize. There you go. Okay, what is the second step of the three-way handshake? And that will be SYN/ACK. So SYN/ACK like this. Okay. Okay, the final question here. So what is the short name for the acknowledgement segment in the three-way handshake? And that is ACK. And we submit. Perfect. Okay, so let's move on to the next task, which is networking tools, ping. At this stage, hopefully all of the theory has made sense and you now understand the basic models behind computer networking. For the rest of the room, we're going to be taking a look at some of the command line networking tools that we can use in practical applications. Many of these tools do work on other operating systems, but for the sake of simplicity, I'm going to assume that you're running Linux for the rest of this room. The first tool that we're going to look at will be the ping command. The ping command is used when we want to test whether a connection to a remote resource is possible. Usually, this will be a website on the internet, but it could also be for a computer on your home network if you want to check if it's configured correctly. Ping works using the ICMP protocol, which is one of the slightly less well-known TCP/IP protocols that were mentioned earlier. The ICMP protocol works on the network layer of the OSI model and thus the internet layer of the TCP/IP model. The basic syntax for ping is what we see on the screen. So in this example, we are using ping to test whether a network connection to Google is possible. So yeah, we can see the image right here, the screenshot, where they're trying to ping a target, which happens to be Google. So we are going to type ping and then google.com, right? Notice that the ping command actually returned the IP address for the Google server that it connected to rather than the URL that was requested. This is a handy secondary application for ping, as it can be used to determine the IP address of the server hosting a website. One of the big advantages of ping is that it's pretty much ubiquitous to any network-enabled device. All operating systems support it out of the box, and even most embedded devices can use ping. Have a go at the following questions. Any questions about syntax can be answered using the man page for ping. So what we need to do in Linux to get the manual page for ping is just type man and then ping. Okay, and now let's answer the questions. What command would you use to ping the bbc.co.uk website? And that will be ping followed by the name of the website, right? So bbc.co.uk. Okay, so let's submit that. Perfect. Now, ping the website that we see right here. What is the IPv4 address? Okay, let's find out. So first we need to start the attack box and just give it a moment. Okay, let's press enter here like this and open the terminal. Perfect. Okay, so let's see the website we needed to ping. Okay, so and by the way, I want to specify how many times I want to ping the website. That's why I'll add the -c switch and the number 1 to the command. That way I'll ping the website once. And if I don't, it will continue pinging the website on and on until I stop it by using Control +C, right? So that's why I'll add, as I said, -c and the number 1 to the command. Okay, so ping -c 1, and let me see, land oracle .co.uk. Perfect, and here is our answer. So let's type that in here. So 217, 160, 0, and 152, like this. So let's submit. Perfect. What switch lets you change the interval of send ping requests? Now let's find out. So for that, we need to open the manual page for ping. So we type in man ping. Okay, let's see. And now let's scroll down until we find the right switch. I already know the answer, of course, but you know, I would like to show you where we can find the answer. So let's see. There it is. So -I. So let's type that in, -I, and we submit. What switch would allow you to restrict requests to IPv4? Here we need to scroll up and we are going to find the answer. Let's see. And there is our answer. So -4. Okay, so we type in -4 and we submit. And the final question here, what switch would give you a more verbose output? Again, we need to scroll down. Let's see. And the attack box is a bit slow, guys, so I have to apologize. Let's see. There is our answer. -V. Oops, let's bring that back up like this. Okay, so this is our answer, right? So -V is the switch. So let's type that in, -V, and we submit. And now let's move on to the next task, which is networking tools, traceroute. The logical follow-up to the ping command is traceroute. Traceroute can be used to map the path your request takes as it heads to the target machine. The internet is made up of many different servers and endpoints, all networked up to each other. This means that in order to get to the content you actually want, you first need to go through a bunch of other servers. Traceroute allows you to see each of these connections. It allows you to see every intermediate step between your computer and the resource that you requested. The basic syntax for traceroute on Linux is this, and we can see that on the screen. By default, the Windows traceroute utility, traceRT, operates using the same ICMP protocol that ping utilizes, and the Unix equivalent operates over UDP. This can be altered with switches in both instances. You can see that it took 13 hops to get from my router to the Google server. And yes, we can see that in the screenshot above. Now it's your turn. As with before, all questions about switches can be answered with the man page for traceroute. And the command is man traceroute. Okay, and now let's answer the questions. So use traceroute on tryhackme.com. Can you see the path your request has taken? Okay, let's find out. Let's go back into the terminal. Let's go out from the manual page for ping. And what we need to do here is type trace, let's see, trace route, and then tryhackme.com, and we press enter. And there you go. So as we can see, we can, yes, of course, see the path, and it took, let's see how many hops. It took 17, right? Okay, so let's just click on completed here and move on to the next question, which is, what switch would you use to specify an interface when using traceroute? Okay, for that, you just need to open the manual page for traceroute. So we type in man, let's try again, let's see, man trace route like this, and we press enter. Okay, and now let's scroll down until we find the right switch. Okay, it's so slow. The attack box is very, very slow. So again, I need to apologize, guys. But yeah, here is our switch. There it is. So -I, right? Okay, so let's type that in. And we submit. There you go. What switch would you use if you wanted to use TCP SYN requests when tracing the route? Here we are going to scroll up until we find the right switch once again. So let's see, there is our answer. So -T, right? So let's type that in and we submit. Lateral thinking. Which layer of the TCP/IP model will traceroute run on by default? Windows. Now, if we scroll up here, we can see half of the answer. By default, the Windows traceroute utility, traceRT, operates using the same ICMP protocol that ping utilizes, okay? And if we open task 5 and look up here, we can see the rest of the answer. So the ICMP protocol works on the network layer of the OSI model, and thus the internet layer of the TCP/IP model. Okay, so the answer is the internet layer. Okay, so let's go back to task number 6 and type in the answer. So we type in internet. There you go, and we submit. And now let's move on to the next task, which is networking tools. Whois. Domain names, the unsung saviors of the internet. Can you imagine how it would feel to remember the IP address of every website you want to visit? Horrible thought. Fortunately, we got domains. We'll talk a little bit more about how this works in the next task. But for now, suffice to know that a domain translates into an IP address so that we don't need to remember it. For example, you can type TryHackMe.com rather than the TryHackMe IP address. Domains are leased out by companies called domain registrars. If you want a domain, you go and register with a registrar, then lease the domain for a certain length of time. Enter Whois. Whois essentially allows you to query who a domain name is registered to. In Europe, personal details are redacted. However, elsewhere, you can potentially get a great deal of information from a Whois search. There is a web version of the Whois tool if you're particularly adverse to the command line. Either way, let's get started. Note, you may need to install Whois before using it. On a Debian-based system, this can be done with what we see on the screen right now. Whois lookups are very easy to perform. Just use Whois and the domain to get a list of available information about the domain registration. This is comparatively a very small amount of information as can often be found. Notice that we've got the domain name, the company that registered the domain, the last renewal, and when it's next due, and a bunch of information about name servers, which we'll look at in the next task. Your turn. Okay, and now let's answer the questions. Perform a Whois search on Facebook.com. Okay, let's do that. So let's go back to the terminal and leave the manual page for traceroute. So we press on Q like this. Okay, and now let's type in Whois and then Facebook.com. Okay, and we press enter. Okay, now let's click on complete it. What is the registrant postal code for Facebook.com? Okay, so what we need to do here is scroll up and find a registrant postal code. Okay, so let's see. We're getting close. Let's see. There it is. Okay, so 94025. Okay, so let's type that in. 94025 like this, and we submit. Perfect. When was the Facebook.com domain first registered? Okay, let's find out. So we need to scroll up and find creation date. I think we got it right. Where it is? There it is. Okay, so here is our answer. Okay, so let's type that in. So 29/03/1997. Okay, March 29th, 1997. Okay, so let's submit. Perfect. Perform a Whois search on Microsoft.com. Note, if you fail to read the above instruction and consequently get the wrong answer for the next question, don't expect a helpful response if you report it as a bug. Okay, no problem. We won't be forced to do that. So let's just do a Whois search on Microsoft. There we go. The attack box is so slow. I'm sorry once again, guys, but there's nothing I can do about it. So okay, so let's do this. So Whois Microsoft, let's see, Microsoft Microsoft.com like this. Okay, and we press enter. Perfect. So we can click on complete it. And now, which city is the registrant based in? Okay, so what we need to do here is scroll up and find registrant city. Okay, let's see. So slow. Let's see, we're getting close. Okay, let's see if we have it right here. Registrant city. Not here. Let's see. Registrant city. Okay, maybe go back down until I think we went past the registrant city section or line. Let's see. Registrant. There we go. Okay, so registrant city, Redmond. Okay, so let's type that in. Redmond. There you go, and we submit. Okay, so next question. OSINT, what is the name of the golf course that is near the registrant address for Microsoft.com? And OSINT, by the way, stands for Open Source Intelligence. Now, when we OSINT, if I can put it that way, we search for and find publicly available information or data that we then use to achieve something, okay? So we can gather that type of information or data from, for example, Google, forums, blogs, social media, etc., etc. You get the picture. So in this case, what we're trying to achieve is to find the name of the golf course that is near the registrant address for Microsoft.com. So first, we need the registrant address for Microsoft.com, and we can see it right above the registrant city. So One Microsoft Way, right? Okay, so let's copy that. We copy. Okay, and let's open Google, or go back to Google and open Google Maps. Okay, and now let's paste the street name in the search field right here. So paste, and we press enter. Okay, and now let's just zoom out a bit, and we will see the name of the golf course in the top left corner of the map, if I remember correctly. Let's see. A little bit more. I think there it is. So here is our answer, right? So Bellevue Golf Course. Okay, so let's type that in. Like this, and let's submit. Perfect. And now, what is the registered tech email for Microsoft.com? Okay, and what we need to do here is scroll down and find tech email. So let's see. Oops, or my bad, scroll up, because now we were at the end of the search we did with the whois. Okay, so let's just scroll back up. Okay, we're getting close. Okay, and here is our answer, right? Tech email, right? Okay, so let's see if I can copy that, or maybe not, because the room is so extremely slow. It's or not the room, but the attack box. It's horrible. So again, I'm sorry guys, really. So let's see. There you go. Let's give it another try. So let's copy that like this, and we paste it right here, and we submit. Perfect. And now let's move on to the next task, which is networking tools. Dig. We talked about domains in the previous task. Now let's talk about how they work. Ever wondered how a URL gets converted into an IP address that your computer can understand? The answer is a TCP/IP protocol called DNS, or Domain Name System. At the most basic level, DNS allows us to ask a special server to give us the IP address of the website we're trying to access. For example, if we made a request to google.com, our computer would first send a request to a special DNS server, which your computer already knows how to find. The server would then go looking for the IP address for Google and send it back to us. Our computer could then send the request to the IP of the Google server. Let's break this down a bit. You make a request to a website. The first thing that your computer does is check its local cache to see if it's already got an IP address stored for the website. If it does, great. If not, it goes to the next stage of the process. Assuming the address hasn't already been found, your computer will then send a request to what's known as a recursive DNS server. These will automatically be known to the router on your network. Many internet service providers, or ISPs, maintain their own recursive servers, but companies such as Google and OpenDNS also control recursive servers. This is how your computer automatically knows where to send the request for information. Details for a recursive DNS server are stored in your router. This server will also maintain a cache of results for popular domains. However, if the website you've requested isn't stored in the cache, the recursive server will pass the request onto a root name server. Before 2004, there were precisely 13 root name DNS servers in the world. These days, there are many more. However, they are still accessible using the same 13 IP addresses assigned to the original servers, balanced so that you get the closest server when you make a request. The root name servers essentially keep track of the DNS servers in the next level down, choosing an appropriate one to redirect your request to. These lower level servers are called top level domain servers. Top level domain servers are split up into extensions. So, for example, if you were searching for TryHackMe.com, your request would be redirected to a TLD server that handled .com domains. If you were searching for bbc.co.uk, your request would be redirected to a TLD server that handles .co.uk domains. As with root name servers, TLD servers keep track of the next level down, authoritative name servers. When a TLD server receives your request for information, the server passes it down to an appropriate authoritative name server. Authoritative name servers are used to store DNS records for domains directly. In other words, every domain in the world will have its DNS records stored on an authoritative name server somewhere or another. They are the source of the information. When your request reaches the authoritative name server for the domain you are querying, it will send the relevant information back to you, allowing your computer to connect to the IP address behind the domain you requested. When you visit a website in your web browser, this all happens automatically, but we can also do it manually with a tool called Dig. Like Ping and Traceroute, Dig should be installed automatically on Linux systems. Dig allows us to manually query recursive DNS servers of our choice for information about domains. And here we can see how the command looks. It's a very useful tool for network troubleshooting. And we have, of course, an example of how it's done in the image that we see on the screen. This is a lot of information. We're currently most interested in the answer section for this room. However, taking the time to learn what the rest of this means is a very good idea. In summary, that information is telling us that we sent it one query and successfully received one full answer, which, as expected, contains the IP address for the domain name that we queried. Another interesting piece of information that Dig gives us is the TTL, time to live, of the queried DNS record. As mentioned previously, when your computer queries a domain name, it stores the results in its local cache. The TTL of the record tells your computer when to stop considering the record as being valid, that is, when it should request the data again rather than relying on the cached copy. The TTL can be found in the second column of the answer section, and we can see that in the screenshot below. It's important to remember that TTL in the context of DNS caching is measured in seconds, so the record in the example will expire in 2 minutes and 37 seconds. Have a go at some questions about DNS and Dig. Okay, let's answer the questions. What is DNS short for? And that is Domain Name System. So let's type that in. Submit. What is the first type of DNS server your computer would query when you search for a domain? And that will be recursive. What type of DNS server contains records specific to domain extensions? For example, .com, .co.uk, etc. Use the long version of the name, okay? And the answer is top level domain. So let's type that in. Top level domain. Where is the very first place your computer would look to find the IP address of a domain? And that will be local cache. Perfect. Now, research. Google runs 2 public DNS servers. One of them can be queried with the IP that we see right here. What is the IP address of the other one? Okay, so let's go to Google and we can just, let's go back. We can just Google Google DNS servers, okay? So Google DNS servers. There you go. Here's our answer. So we can copy that. Copy, and we paste it right here, and we submit. Perfect. And now the last question here. If a DNS query has a TTL of 24 hours, what number would the Dig query show? Okay, so 1 hour is 60 minutes. 1 minute is 60 seconds. So 60 seconds times 60 minutes, that will be 3,600 seconds in 1 hour. And 3,600 seconds times 24 hours, that will be 86,400 seconds. Okay, so the answer is 86,400. Okay, so let's submit. Perfect. And now let's move on to the final task, which is further reading. That's us completed our whirlwind tour of networking basics. Hopefully you found it informative. Networking is one of those things that you just need to learn. We've covered the very basics, but it would be a very good idea to continue to learn by yourself. In terms of further information, feel free to reach out in the TryHackMe Discord if you want any help with the contents of this room. Additionally, if you want to expand your knowledge of networking theory, the Cisco Self self-study guide by Steve McQuarrie is a great resource to work from. There may be a more up-to-date version available, however, this edition is cheap, readily available, and most importantly, still very relevant. Whilst it is designed as a study guide for the CCNA exam, that book serves equally well as a very rounded introduction to networking principles. Okay, and let's click on complete it. And we are done with this room. Okay, everybody, thank you so much for watching. If you enjoyed the video and found it helpful, I would really appreciate it if you give it a thumbs up. And of course, subscribe to the channel for more videos on TryHackMe. Okay, everybody, talk to you next time.